So the question asks about Olaf, who's standing on a sheet of ice, basically, and there's basically no friction on the sheet of ice. So if someone throws a ball at Olaf that weighs 0.4 kilograms, and this travels at 11 meters a second, and Olaf's mass is 69.1 kilograms. So it asks basically in two different situations. Basically, when the ball has an inelastic collision, where Olaf just catches it, and that's kind of the end, and Olaf moves backwards. And the other situation is when it bounces horizontally off Olaf's chest and travels 8.6 meters in the opposite meters a second in the opposite direction. So this is basically an elastic collision where the kinetic energy is conserved. So here is a picture that I drew of it, where Olaf either catches it and it's an inelastic collision, or Olaf doesn't catch it and it bounces off him to be an elastic collision. And as you'll see, this basically changes how the problem is solved. So the strategies to solve this problem are basically to keep the momentum constant, because the law of the conservation of momentum. And the other strategy is to separate velocities during the elastic collision, because in an inelastic collision, basically the two kind of objects basically become one mass, and there's only one final velocity. However, this is not the case in an elastic collision. So in the inelastic collision, we know that the mass of the ball times the initial velocity is equal to the mass of Olaf plus the mass of the ball times the final velocity, because we know that momentum is conserved. So doing this, we can basically solve for the final velocity and then divide by mass of Olaf plus mass of ball. Doing this, we get this little equation here, and we can plug in numbers such as the mass of the ball, 0.4 kilograms, and the velocity of the ball initially. So once we divide this by the mass of Olaf and the mass of the ball, we get the answer of 6.33 times 10 to the minus 2 meters a second. And this is the final velocity of Olaf plus the ball. And in this next one, what we can do is we can basically say that the initial mass of the ball times the velocity of the ball is equal to the mass of Olaf plus times his velocity plus the mass of the ball plus times its final velocity. This is because basically the mass of the ball bounces off Olaf, and this makes it so that Olaf kind of gets more momentum because momentum must be conserved. So this kind of momentum that like the ball that bounced off has must be added to Olaf's momentum to basically compensate and make it so that momentum is still conserved. So basically, using this idea, we can solve for the final velocity of Olaf. But we have to be careful here in knowing that the final velocity for the ball and Olaf are different in this case, rather than the same in an inelastic collision. So to do this, we basically solved for just the velocity of Olaf by doing some subtraction and some division here to get this little equation, plugging in some numbers including mass of the ball, speed of the ball, and the final speed of the ball. We get the value of 0.113 meters a second. And the important thing to notice about this value is that it's higher than the other value. So basically, elastic collisions will have more momentum generated on the object being acted upon, because there's basically another object that's bouncing off, although that's also being acted upon. Like the other object is going to go a little bit faster because it's bouncing off, in this case Olaf. So a common mistake here is not understanding the difference between an inelastic and elastic collision. So basically, in an elastic collision, the kinetic energy is conserved, oftentimes something bounces back in an elastic collision. In an inelastic collision, though, kinetic energy is not conserved. And the inelastic collision makes it so that basically the two objects become kind of one mass and stick together. This is really important, this problem here, because you have to notice that in the inelastic collision part of this problem, both objects has the same final velocity. However, in the elastic part of the problem, the objects don't have the same final velocity, so you have to account for that algebraically. Thank you.